Alrighty, good morning. I'm just writing a question here for you guys. That we can kind of put into perspective with some of the stuff that we've learned yesterday. So, let's say we have a compound that's found to have a molar mass of about 120 grams per mole. And it's also found to be 40% carbon, 6.7% hydrogen, and the rest oxygen. We're going to look at how we can figure out what the formula of the compound is based on this information. The first thing we're going to want to do is figure out its empirical formula. And then we're going to learn today how to then go from empirical to molecular formula based on molar mass. So, first things first, it looks like here we have a bunch of information. We'll use that molar mass bit later on, so we can just kind of forget it for now. To start, it says we have 40% carbon, which is the same thing for us, remember, is 40 grams. It looks like we're going to have 6.7 grams of hydrogen. It says the rest is oxygen, so that means, because this is percentage, we would just subtract the others from 100, right? We would say that oxygen, here, let's write that up here, will be 100 minus 40 minus 6.7. Good morning, happy sunshine. Look, I'll put a B out. That'll make everyone happy. Yay, a B. Okay, there we go. Which turns out to be 53.3, it looks like. So, we can go ahead and put that, 53.3 grams of oxygen. So just like yesterday, remember grams we can never use to compare different substances, so we're going to want to convert all of these into moles. If you were a fan of extra work, you could convert them to atoms instead. Have fun, go right ahead. But while you're doing that, the rest of us will be 3 problems on after that. So I would suggest using moles. So just like before, we're going to use the molar mass of each of these elements to convert all of them into moles. Remember, all these values are from the periodic table. So let's go ahead and... Stream Elements is always so late. That's pretty funny to me. Okay, let's go ahead and do the math here. 40 divided by 12.01. I think we actually did a similar thing yesterday. 3.33. 6.7 is the next one. 6.7 divided by 1.008. Again, I do suggest doing these with your calculator. And then the oxygen, 53.3 divided by 16. It gives us 3.33 again. We would divide all of these by the smallest number. Hopefully we can just see right away that is going to be our empirical formula. CH2O. I think we did do this exact one yesterday, but that's okay. And so now let's go ahead and take a look at that last bit of information that we had in the problem. So remember, empirical formula meant that it was the smallest ratio of things between the elements. So 1 carbon to 2 hydrogens to 1 oxygen. That doesn't tell us the molecular formula, though. It just tells us the smallest ratio. The molecular formula will tell us the actual ratio of everything in our compound. So let's take a look at the molar mass of this guy. Let's find out the empirical molar mass. Empirical, wow, it's a disastrous spelling. Empirical molar mass. And if we do that, it's going to be C plus 2 hydrogens plus oxygen, which will be 12 plus 2 times 1.08 plus 16. Again, I'm zipping through those because I have them memorized. Take your time, look at the periodic table. You know, it's totally okay to take some time there. So doing so, you get about 30 point, what are we going to get? Like 30.0, I don't know, something like that. 3 maybe? Yeah, something like that. And so, what we can do here is let's compare our given molar mass to the empirical molar mass. So let's scroll up in the problem. It's told us that the molar mass of this compound is 120.13. So let's bring that down here. So we have 120.13. And then we have our empirical molar mass. We can see that, hopefully we can see something here. We can see that this is 4, right? It's just 4 times 30.03, roughly. Looks like pretty much is 4. So that tells us that we should multiply our empirical formula by 4 to get the molecular formula. So if we do that, we would multiply all of our components by 4, and we would end up with this would be our molecular formula then. Oftentimes you might see this just written as like something like N, where you are comparing your molar mass that you're given compared to your empirical molar mass. And then that's what you would use to multiply your empirical formula by. So let me just make a little like arrow here. That's going to be your given molar mass over your empirical molar mass. All right, and so that's what you would use to multiply by in order to figure out what your molecular formula is going to be. So just kind of one last step, I guess, that you could throw into a problem. So with that, there's going to be some problems in the textbook you can work through with this. Again, I'll put some worksheets up for you guys. But yeah, this is the end of 3B here. So we're just like about a day or so behind schedule, I think, because of the holiday that we started with, and we've got another holiday next week. So we're gonna have to move on here, unfortunately. But that's okay. We can, you guys can practice this on your homework, and let me know if you have questions. Just so you know, tomorrow again we're going to be doing a review of your exam. So post screenshots of your exam questions in Discord if you want me to go over them. So far, I think we have 3 or 4 or something. It's going to be real short of a review. Totally okay. There's no obligation, of course, to do that. So it's just for you guys. So if you want some help there. Okay, cool. Alrighty then. Any questions on that one, by the way? All right then. Okay, well, in that case, we're going to move on to chapter 4, which is on electrons, or specifically electronic structure. But I like to kind of also include light in this, because we're going to want to talk about light quite a bit as well here. So, we're going to be looking at, right now we've looked at more kind of, atoms overall and compounds overall. We talked about, how to make the atomic symbols and all that fun stuff. But now we're going to go ahead and look at electrons specifically. And remember that electrons are going to be doing, 99% of the chemistry that we see and then take advantage of in chemistry. So electrons are going to be a super important topic. And so we have kind of a lot of kind of detail to go over there. So, but first let's talk about light for a little bit. We'll talk about light and then we'll move into electrons because we're going to see that the two will interact together, and we're going to see that electrons behave similarly to light sometimes. Isn't that nice? Sometimes. So let's talk about light. Light is a wave. Specifically, it is a wave of two components. We have an electric field. Oops. Electric. Oh. Plus a magnetic field. And so light is often described. Why did I put this graph here? We don't need a graph. We often call this electromagnetic radiation. Electromagnetic radiation. Same thing as light. And we're going to see that light, as a wave, has certain properties. Here is a light wave. Waves go up and down perpetually. So we typically, when we look at light, we only focus on either the electric or magnetic components. It doesn't really matter. But they're at 90-degree angles to each other. So if your electric component is going up and down, your magnetic component is going in and out. So that's all we need to know. So we'll just look at one of those. Doesn't matter. Let's look at the electric one. That's fine. Waves kind of have a few components that we talk about. We're going to see we have what's called here a wavelength, which is abbreviated with the Greek letter lambda. That's the distance between two peaks on your wave, or two troughs, or, two midpoints at the same position in a wave. Typically just down at the peaks because it's the easiest kind of place for us to see. That's usually going to be in units of some sort of derivation of meters because it is a length, it is a distance. We also have the amplitude, which technically has some sort of energy unit associated with it, but sometimes we just omit the units. And we're going to see that if we're thinking about light, the wavelength is going to tell us kind of the type or color of light. And the amplitude is going to be related to the intensity of the light. So how bright it is. Yeah. These are sine waves, for sure. Or cosine waves, I guess they're exactly the same. Yeah, so cosine waves and sine waves are definitely how this would look as well, for sure. So the intensity part is going to be kind of like brightness associated with wave, or if you're looking at a sound wave, it would be loudness. And so we're going to see that these two kind of components are going to tell us some of the physical kind of properties of the light. So the wavelength has no kind of bearing on how like strong your light is. However, we often describe this as talking about the energy of the light. So it's not how intense your light is, but how energetic your light is. And we'll look at that further as to seeing what that energy can be doing here. So with those two in mind, we have another component called frequency, which is the Greek letter nu, which stands for frequency. And that is going to be just how quickly the wave oscillates. That means completes a cycle. Per second. So we can see here that the wave just goes up and down and up and down and up and down forever. And basically we're looking at the time, or how often it goes from the top part to the next top part. So basically it's how quickly it moves through that wavelength. And so we can see here that the frequency is going to take some unit of per second, or something called hertz, which is the same thing as inverse seconds. So something like RPM could be done in hertz as well. Rotations per minute. Hertz is just how many per second. And the energy, or rather the wavelength, is done by some sort of meters, right? So let's go ahead and see here. How can we relate the wavelength to the frequency? We're going to see we have a way to do this. So let's think about it. So this is in units of meters. That's in per second. So we have some sort of relationship where we can multiply these to get something that's meters per second. And lo and behold, we do have a factor for us, which is going to be the speed of light. Which is going to be, you don't need to memorize this number, but that's how we relate these two. So we're going to see that the speed of light is a constant number, 3.01 times 10 to the 8th meters per second. And we now have the frequency as well as the wavelength of light. And so we can look at these two and see that because these guys are multiplied together, they're going to be inversely proportional. That means when one goes up, the other one goes down. So if your wavelength goes up, then your frequency goes down, and vice versa. And that kind of makes sense, right? So frequency is how often light can kind of make that distance, how frequently that's happening. And so if your distance is longer, because light travels at the same speed, it's going to only be able to do that repetition, fewer times per second. And conversely, if your wavelength is really small, you're going to be able to go through that wavelength quite a few times as you travel at your speed of light. So let's go ahead and see what this looks like. So, let's say we have a wavelength of, I don't know, 450 nanometers. That's somewhere in the blue light, just so we know. Let me just make that a better frequency. It's not a V, it's a nu. It is a Greek letter, but it looks like V. I get it. So, let's see what the heck this is going to work, or how this is going to work. So, we know that wavelength times frequency will be equal to the speed of light. However, our speed of light is given in meters per second, and our wavelength here is given in nanometers. So we're going to probably want to bring them both into the same unit. Let's go ahead and probably make them into meters. Probably the easiest way to do that. So let's go ahead and take this 450 nanometers, convert it to meters. And if we remember our unit conversions, we'll see that it's 10 to the 9th would be what nano stands for. And so that would be 4.5 times 10 to the negative 7 meters. Just putting that there in scientific notation, but that's good. Alrighty, so now that we have it in meters, we can go ahead and use our formula. So we know that that's how the relationship works. So therefore, nu is going to equal to C over lambda. And so we can say that nu is going to be 3 times 10 to the 8th meters per second over 4.5 times 10 to the negative 7 meters. Meters will cancel out. That's why we had to make sure that we had the correct units there. Otherwise, we'll have something weird happening. Let's go ahead and do this. So 3.01 divided by 4.5. Doing this, you get 6.69 times 10 to the, let's see, that'll be 15, but we subtract 1, so 14. So this wavelength is going up and down 6.7 times 10 to the 14 times per second. So it is very, very quickly going, of course, far faster than I can do mechanically. But that's the frequency of the light. This would also be the same thing as, say, I guess we need 2 sig figs, by the way, so let's just go ahead and do that. Hertz. Hertz is the same thing as seconds, or inverse seconds, so we can do that. If we wanted also, we can say that, hey, we can actually bring this into the, maybe gigahertz. We can talk about that. You've probably seen that on your, internet routers and stuff like that. So let's see what that would be in gigahertz. Gigahertz, of course, is 10 to the 9th, right? Let's see, mega, yeah, giga. Okay, so, and then that would be 1 gigahertz here. And so we're going to see we still have quite a bit. This is going to be a very much higher energy light than we normally see. So that would be 6.7 times 10 to the 5th hertz, or gigahertz, sorry. So we're technically in the terahertz range. So quite a bit more frequent. Just so you know, your Wi-Fi typically operates at roughly 2.4 gigahertz. Or if you have dual band, you'll also have 5 gigahertz. Let's see if we can go ahead and... Oh, by the way, guess what? Wi-Fi is light. It is just light waves. That's all it is. Let's see if we can't take this gigahertz and find the... let's find the wavelength. of this 2.4 gigahertz. Let's see kind of what that's going to look like. So 2.4 gigahertz. Remember, if we're going to use it in our formula, it needs to be in units of hertz, not gigahertz. We just saw that that's going to be 10 to the 9th hertz. And so it's going to be 2.4 times 10 to the 9. Isn't that exciting? That math was very difficult. I was barely able to do it in my head, but there we have it. All right, now that we have it, we can go ahead and use our formula. Remember, hertz is the same thing as inverse seconds. So we know that lambda is going to be C over frequency. So 3.01 times 10 to the 8th meters per second over 2.4 times 10 to the 9th per second. Per seconds will cancel out. And we're going to be left with, let's have a look. So 3.01 divided by 2.4. We have 1.25 times 10 to the negative 1 meters. Something like that. So, our Wi-Fi routers are spitting out light that has wavelengths of just under a meter, so about 10, 12 centimeters long. So, that's, I don't know, something like this, maybe? So, actually a little smaller. Yeah, something like this. So your Wi-Fi router is spitting out waves that are about this long. So light waves can be really, really small, nanometers or meters. We're going to see they can even be kilometers. Radio waves can easily reach the kilometer range, where the distance between your two troughs or peaks on your wave is in the kilometer range. Speaking of which, let's talk about the electromagnetic spectrum. So, we're going to see that we can kind of classify light just according to kind of the range that it falls in. Specifically, we like to take a look at one part in particular, which is the light that we can see. We can see light within actually a very small range. Some insects can go, and then shrimp in that can go way further than we can in terms of sight. But hold on, let me draw my rainbow here. We're kind of pretty limited. Oh dear. Here, let's just have that red go longer, whatever. Okay. The area of visible light that we see is roughly between 400 nanometers to 700 nanometers. That's the light that we can see. That's visible light, and it is all the colors of the rainbow. So we're going to see that purple light is going to be that 400 nanometer range, and the red will be the 700, and the others just kind of lie in between them. And we're going to see that we have, in fact, the whole rest of the spectrum to look at too. We're going to see that we have a number of bits of light that are going to kind of be classified, based on their wavelengths relative to visible light. So we can start with kind of the ones that flank the visible light, ones that we're familiar with perhaps. We're going to see that light that is smaller than 400 nanometers brings us into the ultraviolet range. And that's going to be kind of this area here, if we're looking at wavelength increasing here. So wavelength is increasing as we go left to right. So that's going to be, we're talking about 100 nanometers or so, up to 400 thereabouts, tens of nanometers, somewhere around there. That's going to be our ultraviolet region. And on the other side, we have the infrared, which is going to go to several thousand or 10,000, we'll say, nanometers, something around there. So we go quite a bit into the infrared. So if we think about it, you're probably familiar with the fact that ultraviolet light is definitely harmful to us, right? We have to put sunscreen out when we go out into the sun for long periods of time because UV light is harmful to us. It has enough energy to potentially cause mutations in our DNA that we don't want. Infrared energy, on the other hand, we can kind of feel it as heat. So if you have some object that's giving off heat, like a fire or something, you're feeling infrared light. We can't see it, but we can certainly feel it. And that's going to be less energy than visible light. If we keep on going, here we're going to have the microwaves, which go somewhere in the micro to millimeter range of light here. And then above that, we have the radio waves. Those are going to be, kind of more the centimeters to kilometers or even higher range. So radio waves are light, but they just have very long wavelengths. If we go past ultraviolet the other direction, we get into X-rays and gamma rays. So X-rays, we're going to be talking, 10 to the, minus 10 to the minus 12 or so meters is kind of where we somewhat draw the line between X-rays and gamma rays, where we're getting very, very short. And as we probably know, X-rays are also not something that you want to be zapping yourself with. And for sure, you don't want to have gamma rays blasted at you. You've seen the comics or whatever where they'll turn you into the Hulk or whatever, but not going to happen. You'll just die. So we're going to see that energy is actually going to be going up as we go to the left here. So gamma rays will have the highest energy and radio waves will have the lowest energy. So when you see those conspiracy theories about the 5G radio waves causing mutations and stuff, they simply do not have enough energy to do that. We're going to see that radio waves have very, very little energy compared to things like X-rays. So there you have it. So we're going to see that we can relate now the energy of light along with its wavelength or frequency. And there is a constant that allows us to do that, which is Planck's constant. And we saw just previously that nu was c over lambda. So h is going to be a constant. We're not going to have to calculate this necessarily, but let's see. It's that's Planck's constant there. So it's basically how we can relate energy to the frequency or to the wavelength. So we can see here that energy and frequency are directly proportional. So that means if frequency goes up, then energy goes up as well. Same thing will happen to both. On the other side, we're going to see that wavelength and energy are inversely proportional. And so that's going to say that if we increase the wavelength, then we're going to decrease our energy. So long waves have low energy. and they would also have low frequency. Short waves would be the opposite. Would have high energy and high frequency. So we can see here how to relate those guys together. So I think we've had enough talking about light for now. Suffice it to say, this last bit is kind of the most important, understanding the relationship between wavelength and energy. And frequency too, I suppose. So let's see what the heck the point is. Always a good question. So let's go ahead and here's our kind of fake atom. And let's say it's got 2 rings on it. And we have an electron here. We're going to actually be kind of refining this model of the atom a little bit later, but for now it's pretty easy for us to understand visually. So it turns out that if you zap this electron with light we often write as h nu. Just saying light. Oops, light. What happens is you end up moving your electron to a different orbital. So this electron now has moved to a higher, meaning more energy, orbital. That would be that dot there. After we've given it energy. So, I mean, it makes sense, right? We gave that electron energy. It absorbed the light. Light is energy. If it absorbs that energy, energy can't be created or destroyed. So what's going to happen is that electron is going to move up into a higher energy state, which is going to mean it's just going to move farther from the nucleus. So closer to the nucleus you are is low energy. The farther out you go into higher energy. We often call something like this a ground state, where it was in its low energy, lowest energy possible state. And then this one we would call an excited state, which would just be something with higher energy than your ground state. We often describe, say, hey, we've got a hydrogen atom here that's being zapped with light. Now it is an excited hydrogen. We describe it by putting that little asterisk there to mean that it's in the excited state. Let's indicate that. Excited means it just has more energy. So it turns out that for every different element, each different type of atom, we're going to see that electrons can only absorb certain wavelengths of light. The reason for that is because the energy levels within an atom are fixed. Meaning it takes a certain amount of energy for us to, let's say if this is hydrogen, for us to move that electron from its ground state into an excited state will take a certain exact amount of energy. And it's going to be what's called quantized, meaning you can't just give it any energy you want. You have to give it specific ones. And those specific ones are the only ones that those electrons can absorb. So we're going to see that this is going to, vocab word here is quantized. That means specific energy levels only. So atoms can only absorb light or energy of very specific wavelength. And this is going to be different for each atom. So a hydrogen atom can absorb a certain number of very specific wavelengths. If you look at a helium atom instead, it's going to have a whole different set of wavelengths that it will absorb. And so we're going to see that we can kind of identify atoms this way by looking at what wavelengths of light atoms are absorbing. But before we get into that, let's just see what happens when we have our excited state atom. So excited states are not quite stable. They have higher energy. And so what they'll want to do is get rid of that energy. And remember, energy can't be destroyed or created. So it's just going to spit out that light again. So it is now going to spit out a light wave and come back to its ground state. And we're going to see that the wavelength of light that we put in is the same as the wavelength of the light that we're going to put out. Or at least the energy thereof. We're going to see that sometimes fun things happen. There are other ways that we can remove energy from an electron, but one way to do it is just to spit out your photon again. So your light came in, excited the atom, it hung around in an excited state for a little bit, and then it spat the energy out again, and the electron went back towards the nucleus, back to a lower energy level. And so this would just, we could describe it as back to this. So it's often the case where we can't really see light that we put in, but we can see light that we put out. And so if we just pop over to the textbook here, there are consequences for this. In that certain elements can spit out only certain wavelengths of light. And let's go ahead and take a look at what that means. Yeah, exactly. So we can end up giving a broad spectrum of light to an atom or energy of any type. And we're going to see that what can happen is it's going to spit out only certain ones. Let me just find the video here. That's in our textbook it's one of my favorite experiments to do. Aha. So, let's see, let's pop over here. Let me show this. Aha. So, in this video, there are different samples of different elements in here that are lit on fire. That fire is giving these atoms energy. And we can see that they're burning different colors. Like we have a purplish one here, we've got the green, we've got kind of the orange, and then the red, right? So these are all just different salts, different elements are in there that are on fire, that are being given energy, and they're spitting out different colors. So remember that different colors have different wavelengths. And so, here we can watch that again, I guess. The different colors there are being, we can absorb those by our eyes and interpret them as different colors because they have specific wavelengths. So that red color there has a specific wavelength. That particular shade of green has a specific wavelength. And so that's why we're going to see those particular ones there. So the purple one's always not so good. But just so you know, that's potassium, copper, probably sodium, and then probably lithium for this one. We're going to see it's the metals that have the fun colors, at least that we can see. So, different elements have different energy levels. And so, in fact, there's an enormous amount of things that we can do with this, but perhaps the most fun is fireworks. So when you explode a firework or whatever, you're giving energy to various metals in there that are going to end up giving it those different colors and different textures as well. So, barium is a particularly sparkly one. Oh, they definitely can go all over the place. Yeah. We have very limited vision. We're going to see a lot of the elements will spit out things that we can't see. Like a lot of the non-metals, we're going to see what non-metals are later. Non-metals we typically can't see when they're burned. But the metals just happen to put out ones that are in our range. Hydrogen actually, well here, let's take a look at our good friend Wikipedia. Let's go and see, let's see, what's a fun element to look at? I don't know, let's look at hydrogen. Does it have its thing? Yes. So, we're going to see that hydrogen, if we excite it, is this going to be the right one? Yeah. Hydrogen will spit out, if you can see these lines here, those refer to the colors that hydrogen will spit out. You can see some that are kind of along this range. There are definitely going to be ones on either side as well. And if you end up taking Chem 111, you'll see that we'll be able to calculate these energies based on kind of the energy levels that are happening here. If we want to look at, let's say, a different element, let's look at, I don't know, how about cesium. Cesium, as you can see, being a much more complicated element, has a whole bunch of different very specific lines that it's going to be spitting out. And so we're going to see that kind of each element can be identified by the spectrum of light that it gives out. We saw the hydrogen one's pretty simple. Hydrogen only has one electron, so it can only do a few things. We're going to see cesium has a ton of different energy levels. And you can see some of these energy levels are really close together. Some of them are a bit more far apart. And so we're going to be talking about all that sort of stuff here. So let's go ahead and get rid of this. So there's a reason we're doing all this stuff. So, hooray. There's theoretically no limit to how many different energy levels you have. Though at some point your electron will just be so far away from the nucleus it'll just go away. And you'll have an ion happen. Speaking of ions, gamma rays and X-rays are what are called ionizing radiation. They have enough energy to remove electrons from atoms. So that's why we do not want to be yeah. We're going to see that all of this stuff is related to those shells. Excuse me, for sure. So we'll look at that probably on not Monday, but it's a holiday, Tuesday. So yeah, we'll see for sure kind of how these happen. So, but just so you know, these guys are called ionizing radiation because they have enough energy to remove electrons. So they give electrons so much energy that the electrons just hop out of the atom and they are blasted off to go somewhere else. So X-rays and gamma rays are the most dangerous for that reason. Because we're going to see if you remove electrons, they're going to become extremely reactive species. They're going to react with anything, including your DNA, and mess stuff up. So we don't want those reactions to happen. So we want to avoid X-rays. That's why the X-ray techs will always leave the room when they're zapping you. And that's why you wear a lead shield as well, because that lead is going to absorb a lot of the X-rays. And so like when you go to the dentist or whatever, they put that lead shield on you to protect the rest of your body while just looking at your teeth. So, anyways, yes. So, we're going to see, let's go ahead and answer that question. So we're going to see that a particular atom, oops, is going to have these would be energy levels. Here's a graph of energy. So, as you've pointed out, we're going to talk about what these mean, but there are different kind of like states. These are energy levels in a particular atom. We're going to see that an electron here can absorb light relating to a whole bunch of different things. It can absorb light of energy equal to the distance or the energy difference between n equals 3 and n equals 1. It could absorb the energy difference between the first two. It could absorb the energy difference between the first one and the fourth one, etc. You can have all these different ones. Or we can have an electron in n equals 2 absorbing this much. So, or this much. And we're going to see that these are going to be where all those little lines come from. And so these transitions, for example, n equals 1 to n equals 3, correspond with wavelengths that we can absorb by a particular element. So all of these various transitions can happen, but we cannot do something like this. We can't do something like this where we go in between. Can't do it. You have to go from an energy level to a different energy level. You can't end up halfway in between. So that's not something that would ever happen. So as a result, you're not going to absorb the wavelengths that have the energy of the red arrow. So that wavelength would not be absorbed. It would just go right through, or it would be reflected away or something. That one will not be absorbed. All the blue ones are potential energies that could be absorbed, but not the red one. And so we can have all those different levels happening there. Notice that the difference in energy level also decreases the higher you go. So the difference between n is 1 and 2 is always bigger than 2 and 3, or 3 and 4, 4 and 5, etc. So we're going to see that's also something that we're going to see is pretty common here. So, point is, of all the stuff we've talked about, atoms can only absorb very specific wavelengths that correspond with these energy levels and the distances between them. So we're going to see each atom has its own complete set of energy levels, and we're going to see that's why we're going to have different colors happening in there, and we're also going to see that we can do different kind of chemistry things with these. So, that was a lot of stuff today. I think that's probably as far as we're going to go. No, I can throw one more thing here that's kind of unrelated. No. Let's just do it on. Let's worry about that on Monday, Tuesday, whatever day it is. This is a lot of information. I totally get that. Potentially a lot of new information here. Don't worry. This is probably the most conceptual chapter we have in this class. So a lot of this stuff is just going to be like, do you know it or not, sort of thing, And so on Tuesday we will continue talking about this. We'll talk about how to name these energy levels, how to look at them, how to see where electrons are within them, what energy levels are occupied. And we're going to kind of learn quite a bit about how things are going to be reacting as a result of these electron levels. So that's it for today. Tomorrow we'll have our review session. So if you, again, have any exam questions you want to go over, we can do that. Post them in Discord. We'll have a look. And we'll just go for as long as we have questions up until 10 o'clock tomorrow. Monday's a holiday, so there's not going to be any stream. And then next week we'll probably have another Thursday that we'll do just because we're a little bit behind. So just to make up for these, that sort of thing. Okay, cool. So I'll see you tomorrow if you want. Otherwise, I'll see you Tuesday. Enjoy your long weekend. I'll put your homework up later today. I'll make that homework due Monday just so you can have the weekend to do it since Monday's the holiday. So, alrighty. See you guys.